Over a decade ago, concerns began to grow that silicon semiconductor technology might soon reach its physical limits, particularly as miniaturization reached the atomic scale. This sparked a global search for alternative materials that could sustain the pace of innovation in electronics. Among the most promising candidates are topological materials, thanks in large part to groundbreaking work conducted at the Institute of Physics, Chinese Academy of Sciences, by Chinese physicists Feng Zhong, Dai and Ding Hong.
The exotic electronic band structures of these novel materials give rise to unique surface conducting states. These rare behaviors of the materials, combined with their practical functionality, have opened new avenues for applications in fields including topological quantum computing, low dissipation electronic devices, and new types of spintronics.
In condensed matter physics, researchers study how atoms packed tightly together can give rise to surprising collective behaviors, what they call emergent phenomena. These are effects that can't be predicted just by looking at the individual parts. In 1980, German physicist Klaus von Klitzing made a stunning discovery. While passing an electric current through a thin semiconductor at very low temperatures and under a strong and increasing magnetic field, he expected resistance to increase smoothly, as predicted by the Hall effect. Instead, he saw something astonishing. Hall resistance jumped in precise integer steps. These jumps were unaffected by impurities, revealing the unmistakable hand of quantum physics. 2 years later, Scottish physicist David Thouless explained that this strange behavior used a branch of mathematics called topology. Topology studies how shapes can transform without losing their fundamental identity. Thouless's theory allowed physicists to predict new kinds of electronic structures, topological bands. However, finding real materials that match these predictions proved challenging. Feng Zhong and Dai pioneered computational techniques that brought theory closer to reality. Their methods allowed scientists to predict topological phases in real materials, not just idealized models. From topological insulators to Veil semimetals, their predictions have guided a global search.
At the beginning, finding topological materials to confirm their topological band structure is like searching a needle in a haystack because there are so many different crystals and we have very few clues on where to look for them. The computational method we developed, such as Wilson loop method, make the job easier. So far, we have used them to discover many topological materials, including topological insulators, quantum anomalous Hall systems, and Veil semimetals.
Bridging theory and experiment, Ding Hong and his collaborators used angle-resolved photoemission spectroscopy, ARPES, to prove the existence of an exotic particle, initially predicted by German mathematician Hermann Veil in 1929 in a topological material whose band structure was calculated by Feng and Dai. It was a landmark moment, the first direct observation of these elusive Veil fermions in a solid-state system.
ARPES works by directing a beam of ultraviolet or X-ray photons at a sample to knock electrons out of it, which can then be measured to map the sample's band structure. My team used it to experimentally prove the existence of Veil fermions in the Veil semimetal tantalum arsenic, a type of topological material predicted by the theoretical team led by Feng and Dai.
Their work has sparked a wave of discovery. Today, researchers around the world use their methods to explore new topological phases, accelerating innovation across disciplines. For their contributions to the numerical predictions and the experimental realizations of topological electronic materials, the 2025 Future Science Prize in the Physical Science goes to Feng Zhong, Dai and Ding Hong.